Welcome to the Deep Dive. Today we're tackling a spectrum that, well, you hear about it everywhere in tech circles right now. Terahertz. Our mission today, we've got a stack of sources here, mostly scientific papers, some technical presentations, and we want to really cut through the hype. What is this frequency band, fundamentally? How does it work? And maybe why does it lead to some pretty wild, sometimes controversial applications? So, quick context first. Terahertz sits in this kind of electromagnetic no man's land, doesn't it? Between the high end of microwaves and the low end of infrared light. And here's where it gets interesting, I think. A lot of people assume this is brand new stuff, maybe tied to 5G, 6G. But our reading, well, it suggests this field goes back decades.
That's absolutely right. A really crucial distinction. The commercial buzz might feel recent, but the actual research, not at all. Our sources confirm, dedicated experts have been plugging away at this for 40 years. The groundwork, the initial drivers, they really started back in the 1970s. So yeah, it's not just some flash in the pan buzzword. It's more like a 5-decade evolution in physics.
Okay, so let's get into that physics. We need some ground rules, some definitions. Where does terahertz actually sit on the spectrum?
Right. So technically speaking, the terahertz frequency range is defined from 300 gigahertz or gigahertz up to 3,000 gigahertz. That's 3 terahertz, 3 terahertz.
300 to 3,000 gigahertz. That's a pretty huge chunk of spectrum. What does that mean in terms of wavelength?
Yeah, it corresponds to wavelengths stretching from 1 millimeter all the way down to 100 microns. So, traditionally, this whole area was often just called the sub-millimeter wave regime.
Sub-millimeter, okay.
Yeah.
So what makes that band, that sub-millimeter band, special, energetically speaking?
Yeah, the energy is key. It sits in a pretty low energy regime. We're talking about roughly 1 to 12 millielectron volts MeV. And just to give you a feel for that, this low energy corresponds to really low equivalent temperatures, somewhere between, say, 14 and 140 Kelvin. Very cold.
14 to 140 Kelvin. Why are those specific energy levels, those millielectron volts, why are they important for us, for the audience to grasp?
Because that MeV energy range is uniquely tuned to molecular interactions. It's fundamental. See, when we look at visible light or near-infrared, we're often seeing atomic electrons jumping levels inside atoms, but terahertz waves. They interact directly with the way molecules rotate and vibrate. They probe the chemical structure, the bonds between atoms in a molecule.
Okay, let me just process that. We're talking about a technology almost purpose-built to probe molecules, not just atoms. That sounds like it would be incredibly sensitive for looking at materials, right?
It is, absolutely. And that molecular interaction leads directly to some major advantages. It's why scientists invested so much time and money over the decades. So first up, material interaction. Because it affects molecules, terahertz interacts really strongly with pretty much all states of matter, liquids, gases, solids. And this gives you an extremely high contrast between dielectric materials, insulators, and metals.
Okay. So if you were trying to spot, say, a tiny metal fragment inside a block of plastic, terahertz would make it stand out clearly.
Exactly. And tied into that, certain common materials, think plastics, ceramics, some types of crystals, they're often much more transparent to terahertz waves than they are to visible light or infrared.
Right, so you can see through things you couldn't otherwise.
Precisely. Allows us to peek inside.
That transparency sounds like a huge win for, non-destructive testing or checking things on an assembly line. What else? You mentioned speed earlier.
Speed, yeah. This might be the most technically impressive advantage. Terahertz is just naturally suited for femtosecond probing.
Femtosecond, that's incredibly fast, right? Like a quadrillionth of a second.
Almost impossible to imagine, yeah. A femtosecond is to 1 second what 1 second is to about 32 million years.
Wow, okay.
So we're talking about tracking things like how molecules move, how electric charges shift on these unbelievably short timescales.
Any other big advantages?
Well, a couple more key ones. It's non-ionizing radiation. Unlike X-rays, it doesn't have enough energy to knock electrons off atoms and damage biological cells, which is a big safety plus. And from a practical standpoint, especially for communications, the US FCC hasn't assigned many frequencies above 275 gigahertz, so there's this huge, mostly empty bandwidth potentially available. Vast amounts.
Okay, that list sounds amazing. Massive bandwidth, safe non-ionizing waves, sees through stuff, probes molecules, works at femtosecond speeds. I mean, if the science was this good back in the 70s, why isn't terahertz everywhere now? There must be downsides. What are the constraints?
Oh, there are major constraints. And they're severe. They actually come from the same physics that gives it that molecular sensitivity. The single biggest technical hurdle is loss. Just immense signal loss.
Loss, meaning the signal just fades away quickly.
Very quickly. We deal with really high material losses, both dielectric loss and ohmic loss. Basically, the energy just dissipates as heat when it goes through almost anything. And crucially, get this, there is no equivalent of optical fiber for terahertz. You can't just pipe the signal down a thin, flexible cable like we do with light for the internet.
Ah, no Terahertz fiber optics.
Nope. Any kind of waveguide or cable causes huge attenuation, massive signal drop-off.
So right there, it's inherently a short-range technology, isn't it? Or needs open space.
Pretty much, by necessity. And then adding to that, you've got the atmosphere itself. Water vapor molecules, oxygen molecules, the very things Terahertz is good at interacting with, they absorb the signal like crazy.
Okay, so the air itself fights against it.
Exactly. This atmospheric absorption really limits how far the signal can travel on Earth, maybe 1 or 2 kilometers at the very low end of the Terahertz band where absorption is less. But as you go higher in frequency, you're often down to just meters or maybe tens of meters of useful range. It makes it intrinsically short range terrestrially or, conversely, potentially good for space where there's no atmosphere.
Right, that puts a big damper on long-distance communication ideas.
Yeah.
Okay, let's think about imaging then. You mentioned transparency, but also resolution challenges earlier. What are the practical roadblocks there?
Imaging faces 2 big problems. First, remember that low energy. We're trying to detect these weak Terahertz signals while basically sitting inside a giant, warm, noisy room, which is Earth at about 300 Kelvin. All that background heat, that thermal noise, just swamps the faint Terahertz signal. It leads to really poor contrast in images. It's hard to pick out detail.
Okay, noisy background. What's the second problem?
Fundamental physics again. Wavelength dictates resolution. Because Terahertz wavelengths are much longer than visible light, the smallest spot you can focus a Terahertz beam down to is typically, millimeter scale. Our analysis points out that if you wanted Terahertz resolution to match even a standard optical camera, you'd need an antenna or an aperture that's maybe 1,000 times larger physically.
1,000 times larger. So any high-res Terahertz imaging system would have to be physically huge, or you'd need to be incredibly close to the target.
That's the trade-off, which means high cost. And that high cost brings us back nicely to those traditional applications you mentioned. Where was this technology actually used, given these challenges and costs?
Yeah, where did the money go initially?
Well, the original main driver, the one that got the big funding, was astrophysics. Those unique molecular signatures that Terahertz is so good at detecting, they're crucial for cosmology, for studying how the early universe formed. Terahertz lets astronomers detect specific molecules floating in those incredibly cold, low-pressure clouds between stars and galaxies, stuff you can't see any other way.
So looking for molecules deep in space, how big are we talking investment-wise?
Think big. The European Space Agency's Herschel Space Telescope, launched back in 2009, it carried these massive, complex Terahertz receivers. The mission cost was over $1.5 billion.
Wow. Okay, $1.5 billion to track space molecules? Makes sense. What else?
Other traditional, though still pretty expensive, areas include plasma science. Since the 70s and 80s, Terahertz diagnostics have been used to monitor what's happening inside fusion reactors, like tokamaks, trying to understand that super hot plasma.
Okay, space and fusion, high-end science. But then you get these really specific, almost strange-sounding industrial uses. Non-destructive evaluation, NDE. Why use billion-dollar space tech to count raisins? The source mentioned Raisin Bran.
Haha, yeah, the Raisin Bran example. It sounds funny, but it actually makes sense when you think about the cost of the generation technology back then. It was specialized, expensive hardware. So if you were going to spend that kind of money, the application had to be either, priceless, like cosmology, or something where the unique capability justified the cost in an industrial setting. Measuring raisin content nonstop on a fast production line. That's a high-speed, non-contact quality control problem where Terahertz transparency and sensitivity offer a unique solution. Same for checking if pill coatings are intact or maybe looking under layers of paint on artwork without damaging it.
Right, situations where nothing else works quite as well, so you pay the premium.
Exactly. The unique physics justifies the niche high cost.
Okay, let's touch on the tech that actually makes these Terahertz waves.
Yeah.
Our sources seem to group the generation methods into about 3 main camps.
Yeah, we can break it down like that. First, there's the sort of traditional electronics approach. Take existing microwave or radio frequency, RF, tech, and basically push it, force it to operate at much higher frequencies, extend it upwards. Second, you can use optics. You take powerful lasers and shine them through special nonlinear crystals to convert the light frequency down into the terahertz range, though this method tends to be pretty inefficient energy-wise.
Okay, electronics up, optics down. What's the third way?
The third approach is the one that really opened the field up for more researchers, made it more accessible, relatively speaking. Terahertz time domain spectroscopy, or TDS.
TDS, that connects back to the femtosecond speed you mentioned earlier, right? How does TDS work?
It does. TDS is clever. It uses an ultra-short laser pulse, femtosecond short, and slams it into a special antenna or material.
Oh.
This generates a very brief but very broadband Terahertz signal, like a quick burst containing lots of Terahertz frequencies all at once, but in the time domain.
A short burst of many frequencies. How do you analyze that?
Then you use a mathematical technique of the Fourier transform, it's called. It basically converts that super fast time domain pulse into a full frequency spectrum. It tells you how strong the signal is at each different Terahertz frequency within that burst.
Ah, okay. So instead of needing lots of different lasers tuned to specific Terahertz frequencies, one femtosecond pulse gives you a snapshot across the entire Terahertz band almost instantly.
Exactly. That's the power of it. It allows for really comprehensive material characterization very quickly. You can measure thickness, see how much water is in something, track chemical reactions as they happen, just by seeing how the material changes that broadband Terahertz pulse as it passes through. Essential for probing that molecular world.
Okay, that makes sense.
Yeah.
Now let's pivot. Let's look at the modern push, the stuff driving the current buzz. Communications first. We know long distance is tricky because of the physics, the loss, the atmosphere.
Right.
What about using that huge quiet bandwidth for just short hops? Super high-speed data transfer over short distances.
Yeah, this is where a lot of the serious industrial and, frankly, military investment is focused now. While true long-haul communication probably stays down in the millimeter wave bands below 300 gigahertz, people have shown really impressive data rates using Terahertz frequencies over short distances. We're talking demonstrations of, like, 100 gigabits per second, 100 GBPs. That was done at 237 gigahertz over about 20 meters. Huge speed.
100 GBPs over 20 meters, that's definitely significant, and there's serious money behind this.
Oh, yeah. Our sources specifically call out DARPA, the U.S. Defense Advanced Research Projects Agency. They poured over $50 million just into developing the components, the solid-state tech needed for Terahertz systems. They focused on specialized semiconductor techniques, things like HEMNT, that's high electron mobility, pseudomorphic transistors and HBT, heterojunction bipolar transistors, basically building the tiny high-frequency chips.
So the military and industry clearly see major potential there, even if it's just for short-range, ultra-high-capacity links.
Absolutely. It confirms that recognition.
Okay, let's switch to modern imaging then. We talked about the challenges, the poor contrast from background noise, the millimeter-scale resolution needing huge antennas. How are researchers getting around those problems now?
They're using some pretty sophisticated workarounds. You're right, just simple intensity imaging, like taking a basic Terahertz photo, it generally fails because of those issues. So instead, they lean heavily on advanced techniques, mainly borrowing from radar technology, specifically using radar reconstruction methods with something called FMCW.
FMCW.
Stands for Frequency Modulated Continuous Wave. Basically, instead of sending a single frequency pulse, you send out a chirp, a signal whose frequency sweeps up or down rapidly.
Okay, a frequency chirp. How does that help overcome the contrast and resolution issues where just detecting brightness fails?
FMCW is a game changer because it gives you 3D depth information, range data, for every single point it scans. When you analyze the reflected chirp, you don't just learn how bright the reflection was, you learn precisely how far away that reflection came from. You get depth.
Ah, so it's like radar mapping in 3D using Terahertz waves.
Exactly. This range information is crucial. It lets you build up a three-dimensional picture. You can reconstruct objects hidden behind other materials, like, say, something concealed under a jacket, materials that Terahertz can see through, but visible light can't. That depth perception helps distinguish the object from the background, clutter, and noise in a way that simple 2D intensity imaging just can't manage.
Okay, so using depth and range to effectively see through things that are transparent in the Terahertz spectrum. This capability, I mean, probing molecules at femtosecond speed, seeing in 3D through opaque stuff. This brings us to the final and maybe the most critical points raised in our source material about where all this might be heading, the convergence.
Yeah, that technical capacity, it definitely suggests a potential shift in applications, moving way beyond just lab tools or basic communication into areas like pervasive monitoring. The technical presentation we reviewed, and particularly the commentary around it, it explicitly connects this long line of research, the femtosecond probing, the optoelectronics, to some very contemporary and sometimes controversial concepts.
And specifically, what connections were being drawn in that source documentation. We should be clear, we're reporting what the source states here.
Right. The source material directly links Terahertz research, going all the way back to the 70s, to modern ideas like the Internet of Space Things using these hybrid Terahertz transceivers for new satellite communication networks. But also, much closer to home, concepts like wireless body area networks, W-bands, which involve sensors placed on or potentially in the human body.
On or in the body, okay.
And furthermore, the commentary in the source material explicitly connects this unique Terahertz capability, sensing molecular change at high speed, to things like biometric identity, intra-body communication.
Communicating within the body.
That's what the source suggests is being explored, and even subdermal surveillance, monitoring things beneath the skin.
Wow, okay. And the source proposed a physical mechanism for how that near-body communication might work.
Yes. The commentary claims that this kind of near-field communication, needed for these ultra-short-range body network applications, relies on proximity to what the source referred to as the human biological field, or biofield.
The biofield.
The implication being that the body's own molecular activity could serve as a kind of propagation medium or carry a signature that Terahertz can pick up very close by.
Okay. What else did the analysis mention?
It also detailed that Terahertz technology is utilized for human activity recognition, radar sensing body movement and posture, and for biotelemetry, monitoring biological signals remotely. And it mentioned this duality. Potential positive health applications. The source even mentioned claims about things like rapid cancer cures or mid-beds, alongside potential surveillance systems.
So health and surveillance potential side by side.
Yes. And the conclusion drawn in the source material is that this convergence, these capabilities, they aren't sudden. They're presented as the almost inevitable outcome of 50 years of parallel development across physics, chemistry, material science, and the military and industrial complex driving the needs.
That is quite a journey we've taken in this deep dive. We started off talking about billion-dollar telescopes looking for molecules in the coldest parts of space. And we've ended up discussing source material that talks about technology potentially logging into a body area network using molecular-level probing.
That really is the core tension here, isn't it? The key takeaway for you, the listener. This is a slice of the spectrum defined by this fundamental push and pull. Its physics impose these really significant constraints, the high loss, the atmospheric absorption, making it tough to use. But that very same physics, the interaction with molecules, offers this incredible sensitivity. It lets scientists characterize materials, track changes happening at almost unbelievable femtosecond speeds, which makes it invaluable for certain specialized, short-range systems or for applications out in space.
So let's leave you with a final thought to mull over. Given that terahertz waves are, as we've heard, uniquely effective at measuring molecular changes, and given that this technology, funded by billions over decades, has been evolving since the 1970s. What previously hidden biological processes, things happening down at that femtosecond scale inside us, might now be visible, measurable, and perhaps even targetable thanks to this deep dive into the terahertz gap. Something to consider.